1-3 one-sided limits. So yesterday we talked about just limits at certain points. And there we talked about the thing with limits is we're looking for continuity. Does the function have continuity? If it has continuity, what was that from yesterday? When do we know it's continuous? Say that one more time. When you can't cancel something, okay? Or remember, if you can plug in, if you take the limit as x approaches a number, we'll call the number a. If you plug a in and you get a value without any issues, it's continuous. Okay, so all that means is I can plug in the number that I'm taking the limit of and I can get a value. That's all it means. That means it's continuous. Okay, if you can't, then like Morgan said, we have to do a little bit of work where we have to factor, we have to cancel some stuff, just do a little bit of cleaning it up. That would be a point of discontinuous. Okay, but today we're dealing with, what are these called? Piecewise, right? So we're taking pieces of functions. Okay, so piecewise functions can be continuous or they can be obviously discontinuous. Okay, so if I look at this, say a function is a rule for what is given to you. So what I mean by that is, if I say f of x is this, that's the rules you are given. You have to abide by these rules. Okay, what rules am I talking about? If I give a number less than or equal to 1, I have to use x squared. Does that make sense? So if I'm doing f of 0 and I'm looking at piecewise, am I using x squared or 3 minus x? I'm using x squared. So I'm going to go 0 squared equals 0. Okay, so f of 0 is 0 for that function with those rules. Okay, 1. So which one do I use for 1? X squared, because the equal to, right? So the equal to is on the top one, so I still use x squared, I get 1. Okay, and then f of 2, I get 3 minus 2, so I get 1. Make sense? So we're just abiding by the rules. Okay, so what we're going to do now is we're going to look at this in terms of our limit idea. So remember yesterday with our limit idea, we looked at it from approaching 1 and approaching 1 from the left and approaching 1 from the right. So what it's doing is it's converging to 1. Okay, so I'm going to pause this just for a second. And so again, what I'm doing is I'm looking at longhand. Okay, the limit does, remember, less than 1 means from the left. Okay, less than. Bigger than 1 from the right. So for this piecewise they gave us, from the left, what's it approaching? This one's approaching 1 from the left. Okay, so this one's approaching 1. What's this one approaching? 2. So what does that mean for our continuity? It's not continuous, exactly. Okay, so from the left it approached 1, from the right it approached 2, based on our rules, okay, based on our functions we were given. Okay, so don't confuse yourself like, well, how was I supposed to know that? You just got to figure that out through trying stuff. Okay, we will understand the limit part in a second. Okay, this is a new notation, so you're going to write this. Okay, so for that piecewise, limit as x approaches 1 from the left, you put a negative sign top right. That means from the left of f of x, because that was the function we were given, was equal to 1. So conversely, limit as x approaches 1 from the right with a plus sign upper right, that's from the right, positive, of f of x, it went to 2. No, I'm going to draw the picture in a second. It's not an asymptote. I'm going to draw the picture in a second. What happens is there's a separation at the graph. That's the problem. So I'll show you in the picture in a second. You'll see what I mean by separation. Okay? But what I want you to learn from this for today's lesson is we're going to be evaluating limits from the left and the right. If you do that and you get 2 different answers, that means the limit as x approaches 1 does not exist. Okay, so the limit will not exist if it's two different answers from left to right. That's the main point for today, continuity. It's not continuous. Okay, so let me show you the picture. This would not, because I have a 1 and a 2. They have to match up to exist. All right, so here is what, this is why, Morgan. So here's what the picture of that graph we were just doing looks like. The first one was x squared, just a regular x squared. So we know what that looks like. 0, 0, negative 1, 1, negative 2, 4. Okay, and where did the x squared go to? What was its last number it went to? Like 1, right? It was x less than or equal to 1. So is 1 included? It is. What's 1 squared? 1. So here's the last point of the first piece of our piecewise. That's my first graph. Okay, it's a parabola cut off after 1, because after 1, we're looking at a different graph. That different graph is 3 minus x. So 3 minus x starts up here, but it doesn't actually start here because it doesn't start till after 1, but just, I'm going to put the dot there just to get ready. So it goes over 1, down 1 over 1, because it's negative for a slope, and then it goes down 1 over 1. So the problem is, oh, my dots are off, sorry. Down 1 over 1. Right here, it's an open dot. And you see that's at 2. So this is this is the piece that's not continuous. Okay? It's discontinuous because it's separated. And then this continues to go this way. So this little gap right here makes a discontinuity. Okay? That's why we're proving the limit does not exist, because they're approaching two different numbers. This one, now let's follow it here. This one, let's thin this out a little bit. This one is approaching 1 from the left. This one's approaching 2 from the right. So they're approaching two different numbers, so there does not exist for a limit. That's our point today. Questions? Okay, so by definition here, we just kind of restated it, but if you want to write this down, for by definition, if limit as x approaches a from the left of f of x does not equal limit as x approaches a from the right of f of x, limit, L, big L's limit, does not exist. So I was just saying, if from the left and the right is not equal, it does not exist. Okay, conversely, if limit x approaches a from the left of f of x equals limit from the right of f of x, L exists.
June, your class change.
Okay, that's just kind of the general form.
How do you know if it's approaching from the right to the left?
What do you mean, how do you know if where it's approaching right to the left? Because there's going to be obviously pieces, and so like right here is our connection. So I'm going to take the graph from the left, and I'm going to take the graph from the right. Is that what you mean? Yeah. So it'll be kind of set, if you will. You can always approach things from the left and the right, though, just by trying values. So if it was just one function, I could, like if it was just x squared, I could approach 2 from the left and the right. Like usually 2 would be what? 2 squared is 4. Well, from the left it'd be 4, and from the right it'd be 4, because x squared is continuous. Does that make sense? Yeah. Okay. All right, so let's get to example 1 here. Okay, so example 1, find the limit of x to 0 from the right of square root x. It's kind of a trick question a little bit, but this might even answer Rachel's question a little bit more. of how you know if you're coming from left to right. Can somebody tell me why it's redundant or maybe tedious to ask from the right on this question? Stay there. Right, because I can't come from the left. There's nothing to the left of 0, right? When you're doing a radical, there's nothing to the left of 0 because we can't have negatives. Okay, so that one's a perfect example of it's the only option. Okay, so when you have done that, so notice when I put my notes here, root x only defined x greater than or equal to 0. Okay, root x is only defined x greater than or equal to 0. Therefore, coming from the right, because it looks like this, is the only option. I can only come from this way. I can't come from this way. So if that's the case, we can plug in 0 and we just get 0. The limit is 0. Since we can't test the left side, the right side's all we have, and that makes it exist. So limit exists at 0. It's kind of tricky here. This is a continuous function at 0 because from 0 it keeps going. I know it stops, but it does keep going in a direction. It doesn't break. There's no gaps. Okay, so it is continuous for this example. Okay. Okay, now this one, we'll see if you listen to Mr. Banker at all in Math 20. Okay, so for example 2, we have show that the limit x goes to 0 of absolute value x equals 0. So we're trying to prove that the limit of absolute value x to 0 is 0. Okay, so what do we know about absolute values? There's a positive or negative. So absolute values, guys, are pieces. There's 2 pieces. That's the thing that everybody forgets in Math 20. You get a what? What's the shape of an absolute value graph? It's a V. It's a V, and it's because what happens is this side is negative, this side's positive. It's them joined, the opposites of each other. Okay, so we know the absolute value of x is just that simple V here, 1, 1, 1, 1, negative 2, 2, negative 2, or positive 2, 2, etc. This guy right here is negative x. That's what the line is. It's negative x, and this one is positive x, the opposite of each other. Okay, so knowing that, I can set this up as a piecewise. My piecewise would be x for x greater than or equal to 0, negative x for x less than 0. Because just make one of them, so you don't count the dot twice. I usually make the positive one just because, I don't know, that's what I do usually. Okay, so now we're going to prove this limit exists based on what I taught you already about left side and right side. Because this has 2 different approaches. It has an approach from the left and an approach from the right. Does that make sense? Because they're different lines. Okay, so if I do limit as x approaches 0 from the left of absolute value of x, what will I get? So when I approach from the left, what type of numbers are those? Negative. So where would I look for this? Negatives come from this one, right? Okay, so if I do absolute value of 0 here, if I put 0 in, what do I get? Negative 0 is just 0. Okay. Okay, and then if I do limit as x approaches 0 from the right, okay, so now I'm doing equal to 0, same concept, 0, I still get 0. So we just proved we got the same with each limit from left and right, so the limit does exist. Okay. A little redundant. Okay. All right. We will do a couple more, and then I'll let you guys work on your homework from yesterday. So let's do example 3, and we'll stop there. Okay. So example 3 comes from the Heaviside Function. So you engineers, this will be. I guess you're not going to be electricians. Maybe you will. I don't know. Okay, it comes from like electrical current. So Heaviside Function H, and it's kind of super simple, but we're going to use it just to kind of demonstrate what we're talking about. So H of T represents this like electrical current switch. So at 0, you have 0 current if you are less than time, like if you haven't turned it on. I guess is the best way to put it. And it should be, I think, let me check my notes here. Yeah, so T, so less than 0, and then it's like you have current if you are greater than or equal to 0. Okay, so how this looks is this is what this picture looks like. So right now it's turned off. Your current's turned off. Right when you turn it on, it's immediately on. Okay, that's kind of what that picture is represented in terms of a graph. So it's open dot at 0 because if you haven't flipped it, okay, it's not turned on. As soon as you switch it, it's on. Okay, so now we're going to demonstrate this. Does this limit exist? Well, just looking at the picture, does the limit exist to you?
Yes.
Okay, but if I'm approaching from this way, it's going to tell me what? It's going to tell me 0. If I approach from this way, it's going to tell me 1. Or excuse me, not this way. If I approach from this way, it's going to tell me 1. So it's going to tell me 1 and 0. Okay, so let's just, so it's probably not going to exist. But let's just look at it. So part A here, so limit T goes to 0 from the left of H of T, we get 0. Okay, that's to the left, I would get 0. Anything to the left is 0, I'm going to get 0. So B, limit T 0 from the right of H of T, I'm going to get 1. If I come from the right, that means I'm bigger than 0, I get 1. So therefore, I use this, our book doesn't use this, but 3 triangle dots is the math symbol for therefore. Just so you know. Therefore, limit does not exist. Okay, and that's where we'll start today. So we'll stop there today with part 1.